Now, once you have those key special series memorized, you can do a lot more of these problems a lot more efficiently because you don't have to generate other series from scratch. You can use the ones that you already have memorized and take some shortcuts, as we saw in 9.7. With the polynomials, we're going to do the same thing with the series. So some strategies that we might see is we can substitute into a series for x. So for example, on example 7, we might take this x squared and replace every single x with an x squared. On example 8, we're multiplying by x, and that's this second idea here. We can multiply or divide a series by a constant and or variable. So we can multiply the cosine of x series by x, and we'll just get a new series. This is definitely better than taking repeated derivatives, because for both of these examples, example 7 and example 8, repeated derivatives will get pretty painful pretty quickly, with chain rule and product rule making things very time consuming and tedious. So these are some very good shortcuts that we're going to want to know. So definitely memorize the sine of x. We know that the sine of x is equal to the sum from n equals 0 to infinity of -1 to the n times x raised to the 2n plus 1 over 2n plus 1 factorial. And that's true for all values of x, because you can check in the ratio test that this series converges for all values of x. Now this is equal to, we can write out the first 4 non-zero terms in the general term. We've got the x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. And that's the first 4 non-zero terms. The general term is found here in the summation, so I won't write that down again. Now, if I'm going to now ask, what about the series for sine of x squared? Well, we just replace every single time we see an x, we replace it with an x squared. So we've got not x to the 2n minus 1, but x squared to the 2n minus 1. Let's see, so if we have x squared raised to the 2n plus 1, then we can just multiply that 2 times the 2n, and we can multiply that 2 times the 1, and when we distribute that through, we get x raised to the 4n plus 2 over, that denominator isn't going to change, that's going to stay 2n plus 1. And that's the general term. And then the first 4 non-zero terms, well, we're just going to replace each x with a x squared. So that x becomes x squared. That x to the 3rd becomes x to the 6th. That x to the 5th becomes x to the 10th. That x to the 7th becomes x to the 14th. Notice that the denominators don't change, just the exponents in the numerator. And it would behoove you to expand this out and verify that when n equals 0, we get this. And when n equals 1, we get this, etc. And if you do verify that, then you have some confidence that you've done this correctly. And I believe it looks like this is working out right. So anyway, that's the nice shortcut, so we don't have to worry about, again, just as a quick reminder, if we had done this the long way, the sine of x squared is what we're starting with, and f prime of x would be cosine of x squared, oops, cosine of x squared times 2x. And then the second derivative would be yucky, right? We've got 2 times the cosine of x squared minus 2x times another 2x times the sine of x squared, because of the product rule, and that's just yuck. So we don't want to do that. So let's find these shortcuts and use them to our advantage. For this next one, again, we have the cosine of x memorized. We know that the cosine of x is the sum from n equals 0 to 1, or no, 0 to infinity, of -1 raised to the n. This time we're only going to pick the even numbers, so 2n and 2n factorial. So that's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus and minus, etc. So that's the first 4 non-zero terms and the general term of the cosine of x. Now if we multiply everything by x, then we get x times the cosine of x, which is what they asked for here. And over here we're going to say, well, let's see, everything stays the same. Everything here stays the same, except we're multiplying by x. So instead of x to the 2n, we've got x to the 2n times 1 more x. So that's going to be x to the 2n plus 1. And the denominator, again, does not change. So we'll multiply the first term times x, multiply that second term by x, multiply that third term times x, and we'll multiply that fourth term times x. And we're done. Sure beats repeated product rule. All right, another thing we can do, number 3 here says add or subtract 2 series. That's what we're doing on the 9th example down here. Again, we know what e to the x is. E to the x is the sum from n equals 0 to infinity of x to the n over n factorial. That's the nicest one. And x to the negative, or e to the negative x, we can find that one pretty easily, because all we have to do is change all of our x's to negative x. Make sure you use parentheses here. That is essential. And so this is, let's see, we've got 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. And then down here we've got something alternating going on, right? We've got 1 minus x over 1 plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4 over 4 factorial. And we're going to have to add these two together for this problem. Okay, well, we can do that, but what's going to end up happening is these guys are going to cancel out, and these guys are going to cancel out, and all the odd ones are going to cancel out. So when we take the sum, e to the x plus e to the negative x, we're going to get 1 plus 1 is 2, and x squared plus x squared is 2x squared, and x to the 4th plus x to the 4th is 2x to the 4th. And that's only the first 3 non-zero terms, and we want the first 4, so we can follow this pattern and get one more here. That's going to be 2x to the 6th over 6 factorial. And now it says to divide that by 2, so when we divide that by 2, we'll divide this by 2 as well. And that's going to cut everything in half, and we're going to get back down to coefficients of 1 in the numerator. So this should be what we end up with. So we know that e to the x plus e to the negative x divided by 2 looks like we're going to have just the even exponents. So we've seen that with the cosines. So we've got n equals 0 to infinity. There's no alternating going on here. It's all positive. So we just have x to the 2n over 2n factorial, right? When x equals 0, we get 0. So x to the 0 is 1. And 0 factorial is defined to be 1. When we let n equal 1, we get x to the 2 over 2 factorial. That's our second term. When we let n equals 2, we get x to the 4 over 4 factorial, which maybe I'll make that a little bit more legible. X to the 4 over 4 factorial. That's when n equals 2. And when n equals 3, we get x to the 6 over 6 factorial. So it actually ends up to be a fairly straightforward answer. All right, so those last two techniques, 4 and 5. We did a little bit of 4 above with e to the x. We differentiated and integrated the series for e to the x. And we've kind of hinted on those geometric power series as well a few times in the class. Those are going to be hit pretty hard in section 9.9, but you don't have to worry about those yet. So worry about those other strategies that we're looking at here in these last 3 examples, where we're replacing x with something, or multiplying our series by something, or perhaps adding 2 series together.